Good morning, Strange Loopers. Welcome to Complexities of Color and Computing. My name is Wondra, and I'm real excited to talk with you today about color and all the weird, wonderful parts of it that we don't really think about in our daily lives. Are y'all having a good weekend? Like, woo! All right, thanks for joining me on this beautiful Saturday. First, can I ask, did anybody actually bring any handwork, any like knitting or cross-stitching? Yeah, all right, I love it. Okay, oh, wait, hold on. It helps when you actually start your slides and then you can click through them, maybe. The second complexity of color and computing is that sometimes you start your slideshow wrong. Okay, we're gonna be drinking from the fire hose a little bit in this high-level survey on the principles of color, and kind of depending on your starting point, it might be a little bit overwhelming. My main hope is that at least glimpsing some of these processes and potential complications behind what color is, how humans perceive color versus how machines perceive color, and some of this history will help you as you go forward in your own technical journey. I'm also hoping to give you some technical tips and talk about some current use of color, especially in textiles and counteracting things like facial recognition, which just happen to be some of my own personal interests. I do want to note at the top, before we dive in, that we are going to talk about racism a couple of times, mostly in historical context and in the context of facial recognition. This is not a talk that is about racism, but it did come up in my research several times, and as a white woman who does benefit from systemic racism, omitting it from this talk would be perpetuating it, so I decided to leave it in. In my personal experience, understanding some of the forces behind what makes something work, even if not everything sticks, can really help me write better, more accessible code in the future, because I know why that rule is there, even if I don't remember all of the specific pieces of the puzzle. Okay, so a little bit about me. So we have a starting point for this whole thing. I'm Ellen, as I said at the top. I'm from Illinois originally, but I'm currently based out of Tacoma, Washington. I was in the inaugural class of the Ada Developers Academy, which is a code school for women and gender diverse individuals. Before I was a developer, I was a crafter. And I learned how to process algorithms by going to Michael's Crafts and going to the clearance rack and getting knitting needles and yarn and taking the string and figuring out how to turn it into cloth. I dabble mostly in fiber arts, some of which I did include here. Lately, I've been playing a lot with cross-stitch. I created on the right, let's see, up above you can see a completed cross-stitch that I created on the right and a pattern that I generated on the left with my Stitchifier gem, which is something that you can find on GitHub for reference. Many handwork patterns do look like this, like blocks of color or shapes arranged in clear patterns. So a few years ago, when an ex-girlfriend challenged me to create a ruby gem that converts pictures to cross-stitch, this task seemed really simple. I would just need to cut an image into a grid and compare the colors in the sections of the grid with my available colors of thread, which I naively thought wouldn't be too hard. But in order to do that, I had to learn a lot more about color, and I'm gonna pass some of that knowledge on to you. So first, what actually is color? Easy. It's just energy waves grouped on the electromagnetic spectrum. Boom. Okay, this honestly reminds me of my first day in code school when my instructor described Git as a directed acyclical graph and then also did a little mic drop, luckily also as a joke. In nature, color starts out as white light, containing all of the colors on the electromagnetic spectrum. When this light hits objects, it bounces off of those objects, and some of those wavelengths are absorbed. The remaining, still moving electromagnetic waves continue on and they hit your eye, giving an object a color. This is what we call color subtractive. The white light contains all of the color until we subtract certain colors to arrive at our final color. So let's anchor this in a real world example. Let's look at these lovely flowers that my roommate got last week. The same white light, containing all of the colors of the same groupings of the electromagnetic wavelengths, hits those flowers, but then the different flowers absorb different wavelengths of light. The red flowers absorb most of the light that was sent to them, leaving just a loose wavelength of red remaining to bounce back into your eye. The purple flowers, on the other hand, don't absorb much at all. They absorb a couple of wavelengths and send on a very short wavelength of purple color onto your eye. Sometimes this energy is enough to translate to noticeable heat as well. Anecdotally, when I taught this lesson to my roommate in preparation for this talk, and casually mentioned that this heat factor does sometimes occur, he was shocked to discover that the red flowers were in fact warmer than the purple flowers. I did mention a few times that this light then bounces from the objects to our eyes. So how does the human eye actually see color? Well, once the light enters the eye, the lens at the front of your eye focuses the beam so that it hits the retina on the back of the eye, which is a part of the optic nerve. Notably, if you're near or farsighted, you may use glasses to perfect the lens's aim, like me, hey, so that the light really focuses on the retina instead of focusing in front or in back of the retina. The retina then has specialized cells called rods and cones. The rods are sensitive to light, but not to color. This is why we don't see color as well in the dark. The cones are sensitive to changes in color. These cones are themselves specialized, and each type of cone is more sensitive to changes in red, green, or blue. There are exceptions, of course. If there is damage or corrosion to the optic nerve for some reason, or if you lack the gene that's required to provide the optic nerve with the right pigments of color, you might end up partially or completely colorblind. This means that your brain can take two completely different wavelengths of color and interpret them as if they're the same. Weirdly, this is our first foray into racism for the day. There's a statistic that gets tossed around a lot when you talk about being colorblind, and that statistic is 8% of men and 0.5% of women are colorblind. But what the articles usually don't tell you is that this study was done on people with Northern European ancestry. I spent a lot of time digging around on the internet trying to find a study that actually was broader than the specific Northern European ancestry number, and I couldn't find it. So we don't actually know how many people are colorblind. It could be fewer than 4.25% of the population, but it could also be a lot more. We just don't know. The data is not there. Regardless, though, we know that IE11 is the most popular version of Internet Explorer currently in use, and it was only 2.61% of the market share of browser clients in August of 2019, sorry. The most popular IE browser is around half as popular as being colorblind. So we should be paying attention to these variances in color vision when we code. Okay, so that's the human eye. Pixels work a little bit differently, however. Instead of a ray of light from a third-party source bouncing off of an object, pixels create color by using 3 tiny bulbs against a black background. Each color is turned on in some intensity between 0 and 255. These 3 colors in combination make other colors. We call this additive color because the color is created by adding light together instead of splitting light apart. Most pixels use RGB, which means red, green, and blue. There's a couple more computer color spaces that come up a lot, including sRGB, which is the standardized RGB, hexadecimal, which is a way of representing RGB, CYMK, which stands for cyan, yellow, magenta, and black, which you can see here too, the cyan, yellow, magenta, and black that have been created in the intersections of the green, red, and blue, it's a color subtractive method of measuring color, and HSL, which stands for hue, saturation, and light. But for the purposes of this talk, however, we're going to focus on RGB, since it's based on the physics of the eye, but it also reveals a lot of the limitations and interesting cliffs in our understanding. Say, for example, in comparing the distance between 2 colors. Okay, so now we have some pixels. Let's do something with them. Let's say, for example, you're trying to make a cross-stitch pattern of Supreme Court Justice Ruth Bader Ginsburg done only in the colors red, blue, and green, because you keep confusing RBG with RGB for the biggest conference talk of your life to date. You found a great picture of her online. You've divided that picture into a grid of pixels, and now you just need to determine which of the pixels is closest to these 3 colors you've got, and you can make an RBG RGB masterpiece. Euclidean math to the rescue, right? My initial thought here, along with the initial thought of many an optimistic programmer, is that we can use Euclidean math. So here we say that R1, G1, B1 is the color value of the pixel we're looking at, say in her lovely eyes. And R2, G2, B2 is the color value of the second pixel, or in this case, one of the threads I'm sewing with. Then the distance squared is R1 minus R2 squared plus G1 minus G2 squared plus B1 minus B2 squared. So I can check the distance between each of the colors, see which one has the shortest distance, and decide, okay, I should pick that color for that pixel. It turns out, however, that the answer is a lot more complicated than that. The human eye is a lot more sensitive in changes to illumination than it is in changes in color. It's also more sensitive to changes in dark tones than it is to changes in light tones. Originally, as color scientists were first discovering this, they attempted to weigh the RGB values and stick to a mostly Euclidean algorithm, XR, YG, ZB. But it became clear that it simply was not complex enough to reflect the way the human eye sees color. So in 1976, the International Commission on Illumination first standardized the value of delta E. Delta E is an alternative algorithm for describing the distance between two colors. It has been changed several times throughout the years as the ability to depict color on a screen has advanced, along with our understanding of color. After the algorithm has been applied, it describes the difference between two colors as a single number. Now, originally, I was going to show you the formulas for delta E, a few of them, but honestly, most of the articles that explain delta E to you don't even attempt to show them to you. They just send you a link to a converter. Like, they just say, don't even try to do this yourself, find someone else who's already done it. It didn't seem helpful to show these to you, just intimidating. So suffice it to say that there is an entire branch of color science devoted to exploring why twice as much blue does not look the same to the human eye as twice as much yellow. This nonlinear processing of visual information comes up again in photography in particular, which is an issue when we're making our RGB masterpiece, remember. It comes up in a concept called gamma correction. Since the human eye is so much more sensitive to the differences in shadows than it is to the differences in light, but digital cameras default to linear storage and prioritization of light, unencoded images would store light at a linear rate, which leads to some unattractive images that don't pick up on detail in the shadows that our human eyes perceive, and that do pick up on details in bright areas that our human eyes do not. Luckily, practically all digital photography now uses gamma encoding, which is algorithmic encoding that defines the relationship between a pixel and its actual luminosity. This means that similar to this idea of delta E, it uses the available modern knowledge of the eye and the properties of the hardware taking the picture to make adaptations in the encoding when the picture is taken. It's more efficient and it looks a lot better too. I do want to note here that yesterday, John Austin did a great talk called RGB to XYZ that went into gamma correction in much more detail, and it did it really well. So I highly recommend that you check that out and go back and watch that talk if this concept interests you. I know I talked about it for one slide. You went into it in great detail, so highly recommend checking that talk out. Okay, now as I mentioned earlier, being colorblind is more popular than using Internet Explorer 11. So let's talk about some areas of accessibility and some access background. The Web Content Accessibility Guideline has a few suggestions for building accessible websites accommodating for contrast and color. The WCAG extends the, you know what, I'm gonna drink water for a second. This is a real weird transition. Sorry, y'all. I'm a weird kind of lady, so sorry. This is the choice you made when you sat down here. Okay, now that I've taken a moment. Okay, the WCAG extends the Americans with Disabilities Act of 1990. So it's 1990. The ADA is a civil rights law that prohibits discrimination against individuals with disabilities, like me, in all areas of life. So that was in 1990. The internet wasn't available for public use until August 6th, 1991, And it didn't become the behemoth capable of running or ruining our lives until much later. So it's not terribly surprising that the ADA didn't predict the internet, a year early. So enter the Web Content Accessibility Guidelines. WCAG was first published in January 1995 as part of the Web Accessibility Initiative of the World Wide Web Consortium, which sought to put together some clear, simple benchmarks to make websites more accessible, not only for disabled individuals, but also for all users on unusual devices, including cellular telephones. They were updated in December 2008 when they became the WCAG 2.0. As of June 2018, WCAG 2.1 became the new recommendation, though it is not yet the adopted standard, and many websites still fail to meet these standards. The developers who created Beyonce.com, they are currently in the middle of a class action lawsuit because you cannot tab through that page, and the WCAG was cited. Amazon.com is currently in the middle of a class action lawsuit because of similar reasons, and the WCAG is cited there too. And in June of 2019, the Times reported that every single Democratic candidate for president failed the accessibility standards listed in those guidelines. Every single one. So the Web Content Accessibility Guidelines touch on many different parts of accessibility, but since we're talking about color, we're just going to talk about color and contrast. So the more straightforward requirement is that color is not used as the only visual means of conveying information, indicating an action, prompting a response, or distinguishing a visual element. So like the first example that comes immediately to my mind is like an input box. So let's say you have an input field and you're expecting something serious, some valid input, and instead you get something goofy. If you are not thinking about it, you might just indicate that it's invalid input by changing the input box so that it's red. But not all users are going to be able to tell the difference between a red input box and the input box that was the color that it was initially. This doesn't work for everyone. So that's why color cannot be the only means of conveying visual information. Adding additional details like, say, an error message, a warning icon, a stripe, a heavy outline, and disabling the button, some of which I've done here, are great ways to visually denote outside of color that something is different with the data provided. Regardless, you just should not have color being the only way that you are indicating to the user that something is wrong or incorrect, or that they should be doing something different with that data. Okay, on to contrast requirements. With a couple of exceptions, the WCAG AAA requirements for minimum contrast between text and background on a page is 4.5 to 1. Now remember, this is a minimum and not a recommendation due to all the stuff we talked about earlier about interpreting some colors differently than others. Not all of these are going to look the same or look equally good, so you should still use your best judgment. Let's see. Beyond that, you can also use things like font size, shape, and style to increase readability. Those exceptions that I had mentioned just a moment ago are about things like increasing the font size that can change the contrast requirements. So the guide itself gives you more recommendations to make your text more readable. The WCAG AA certification requires a 7 to 1 minimum text contrast, and the WCAG 2 to 1 added new level AA requirements for non-text user interface components and graphic objects that requires that adjacent items have a contrast ratio of 3 to 1 in order to pass. This just means that if you make a really cool logo, but it's all in a bunch of shades of blue adabadia, adabadia, then it's probably not gonna pass. A monochromatic blue, fun song logo sounds like a great idea, but again, if it is a logo and you are trying to convey information just in one color, even if that color is blue and a silly joke, then you're trying to convey information with color, and you should not be doing that unless you have the correct contrast ratios. Okay, the thing we need to remember though, because those are all the requirements for contrast and color. That's it. that they've listed. The thing we need to remember is that there are always going to be axes of access that we are not thinking about. We're always going to be behind. And that has absolutely been true and apparent in the history of color. And one great example of this is with the Shirley cards. So in the 1950s, Kodak sold almost all of the color film used in the United States. In 1954, as part of an agreement to break up their monopoly, they developed a printer that's small enough to fit in stores. So this is like what led to being able to print photos in your Walgreens and your CVS today, right? And they decide that they need a test to help store employees decide if the printer has the proper balance of ink or not. So each printer also gets a negative of a store employee named Shirley and a copy of a card that has been printed at HQ. The stores were told that once the printers could make Shirley look good, the printers were balanced. However, they didn't think about the fact that Shirley was a very pale-skinned white woman wearing light-colored fabric on a light background. It turns out that you need a lot more red ink in your printer if you're printing pictures of people with a darker skin tone, or pictures with people with a variety of skin tones in them. But because they never tested their printers on anyone but this very pale-skinned woman, they didn't think about it. They didn't think about it, and they didn't update the Shirley cards for 20 years to include people with a variety of skin tones. 20 years, the 1970s. So think about that. That means that for 2 decades, light-skinned people had access to easy, affordable photography and printing, and example cards that included the word normal in them. You can see it right here, it says normal. And people with darker skin did not. All because Kodak made some bad choices, and as a result, their printers didn't have enough red ink in them. Now, you'd hope that after we saw the evidence of what 20 years of racial bias and test data can do to your outcomes in color, we would be better at this. But we can see plenty of evidence today that we are still ignoring the lessons of Shirley, particularly in facial recognition software, which is notoriously unreliable. According to studies put out last year on the major facial recognition software programs, including algorithms from Amazon, IBM, and Microsoft, there were extreme differences on the quality of facial recognition matches depending on your gender and especially your race. Sorry, I lost my spot. It's like, I have strong opinions on this, and then while white men had a near perfect match rate, there was a near 20% failure rate for dark-skinned women, which is an astronomical difference. It's hard to tease apart how much of this is racism, but it's a lot. We know that the data sets that they're using to test their facial recognition software before it gets put into production are not including enough dark-skinned and not enough female faces. And beyond that, some of it's color science and some of it is inclusion. There are real-world consequences to continuing the mistakes of Shirley's day, though. In 2009, HP released a printer that was supposed to use facial recognition to track users, but as you could see in a viral video titled "HP Computers Are Racist," it could supposedly only track you if you had light skin. In 2017, the iPhone X used facial recognition to unlock phones, but then it had to start issuing refunds to Chinese customers because their phones couldn't tell them apart. Today, we use unreliable facial recognition to enable mass incarceration. Racist data sets have racist consequences. We could and should have an entire conference on that premise alone. But like I said, this is a talk about color. I'm a little pasty to be qualified to do a deep dive here anyway. So we're gonna move on and get back to the color. So let's talk about some of the ways that we've used color to encode information. Now there's a long and proud history of using color and fabric to innocuously hide information in plain sight, especially among knitters. Sometimes it was to hide access. So there was a spy during the Revolutionary War called Molly Old Mom Rinker, who would sit on a hilltop and pretend to knit. And she looked innocuous enough that folks would let her be. They'd just leave her alone because they figured she was just an old lady knitting. and that allowed her to spy. There's also a long history of women in particular knitting code into fabric. So in both World War I and World War II, knitters living by the railroads were powerful forces for the resistance because they were able to work innocuously, knitting code in purled and knit stitches that meant absolutely nothing, just looked like random bits of fabric to people who didn't know the code, but then they could hand this scarf off to someone who understood it, and it told them the movements of the opposing troops, which is astounding and amazing to me. And then today, there's still plenty of crafters following closely in their footsteps, actually knitting and crocheting code directly. And I myself have stitched more than a few QR codes as well, but I'd like to focus more on their spiritual descendants, the counter-surveillance wearable. I'm gonna take another water break. Thanks for hanging. Okay, there's a few details to the counter-surveillance puzzle to talk about before the examples. So first, what I'm talking about is largely ways to counter facial recognition using color. So to understand how this works, you need to know a little bit about how most facial recognition works. So while Apple is currently working with depth, sorry, wrong way. Apple is currently working, going off of depth, so facial depth, but most of the facial recognition is working with light, and it uses specific points on your face, largely your T-zone, which is like here and here, and then the shape of your jawline to establish the existence of a human face shape. And then once the software scanning for faces has determined like, hey, there's enough color points over here in this grouping that I think looks like a face, then it hits a database of known faces looking for a match to the mapping of specific colorful dots and lines that it's found. So counter-surveillance wearables largely attack one or more of those points in the process. They hide the T-zone, they reshape the jawline, they change the grouping of these recognizable dots, or they hijack the database hit. So these are a couple of my favorite examples of hiding the T-zone and the jawline. So on the left, you have an example of CV Dazzle, which is a project created by the avant-garde artist and computer scientist Adam Harvey. He created both a set of instructions and a full lookbook set of computer camouflage, carefully deconstructing the face and the T-zone. He broke down the use of enhancers. He's against them because they attract light to specific points on your face, and has mathematical models and impressive and clear scans showing the effectiveness of his carefully thought out methods and his years of work. And then on the right are the members of the Insane Clown Posse. Their fans, called juggalos and juggalettes, have a distinctive makeup style that they favor, and it turns out that that makeup style just happens to reshape the jaw and obscure the T-zone enough to break facial recognition, as Ticketmaster found to their chagrin when they attempted to use facial recognition to speed up ticketing at an Insane Clown Posse event. So. There's also some more subtle takes on using color to update facial recognition software, however. A team out of Carnegie Mellon developed some glasses that have dots in certain areas that to humans just kind of look like a maybe slightly childish fashion statement, but to software looks like a subtle remapping of those specific dots on your face, and that can actually make the facial recognition software think that you are a completely different person. So the researchers were successfully able to trick the software into thinking that an adult male researcher on their team was the actress Mila Jovovich. And for an even more subtle look, a team in Hong Kong is using the same principles of remapping those specific and identifiable dots on your face, but working outside of the visible light spectrum. So they have LED lights in baseball caps on the bill of a baseball cap that shine infrared lights on their faces. They update the look of their face in ways that are easily picked up by facial recognition cameras as facial details, but they're completely invisible to the human eye. Easily my favorite, however, is another piece that comes from Adam Harvey, who, as we remember, he did CV Dazzle, in collaboration with Hyphen Labs' Neurospeculative Afrofeminism project, which is a transmedia exploration of the lives of Black women and the roles they play in technology, society, and culture. The idea behind this piece, which this is a prototype, in case you could not tell from it saying prototype, is instead of obscuring the face and hiding, which might potentially make you more vulnerable in human ways, if you have a very obvious facial obscuring something, then humans might detect that, then you wear a pattern like this, which is cleverly designed with the kinds of dots and shapes that we were talking about earlier that facial recognition software recognizes as faces. So the software sees the scarf, sees hundreds or thousands of potential faces, attempts to make hundreds or thousands of potential matches, and is overwhelmed and it crashes just because of this innocuous looking Afrofuturist scarf. Okay, so to kind of bring some of these pieces together though too. Do y'all remember the dress? The dress right here? So here's the story for anyone who doesn't or who didn't know anything of it beyond, hey, what color do you see this dress as? So back in 2015 in Scotland, a couple was getting ready for their wedding, and the bride's mother was looking for a dress to wear to the event. So she took a picture of the dress she liked, and she sent it to her daughter for consideration. And the daughter replied that she really liked the gold and yellow one. And the mother is baffled because she did not take a picture of a gold and yellow dress. She took a picture of a blue and black dress. So a family friend thought this was real funny, that the dress looked very different to the two different women. So she puts the picture online and it quickly goes viral because it turns out that according to one study, only around 28% of people see the dress as blue and black, while 68% see it as white and gold. So here's the real kicker. Today, 4 years later, we don't actually know why this phenomenon occurs. So while I was researching the dress, I read a number of different articles that said with certainty that they had the answer. And most of them cited reliable but small trends, but they did not know how to replicate this effect. So most of the studies agree that the dress phenomenon has something to do with the assumptions that we make when we look at this picture. For instance, some people look at the picture and automatically assume that it was taken in bright sunlight based on the light spot that you see in the upper right corner. There's some decent evidence that if you believe that the dress picture was taken in the sun, you're more likely to mentally subtract blue from the picture because sunlight overrepresents blue because the sky is blue. And compared to incandescent light bulbs, it overrepresents blue. So then that makes you see the dress as white and yellow because you're mentally taking that blue color away from it. But the truth is that, and there's also some correlation between the typical light wavelength that the viewer is exposed to. So if you're a night owl versus a morning person, there's like a 4% correlation between how likely you are to see the dress as blue and black versus white and yellow. But the truth is that the sheer number, variety, and blind confidence of articles claiming that they know the truth of the science behind the dress is further evidence that we really do not understand it. So imagine that we had an accessibility issue that depended on seeing this dress as blue and black and not white and gold. Let's say there was a logo that we had in this image. We could not solve it because we just don't understand the science well enough. If we had a security vulnerability that depended on not letting that dress ever go white and gold, we couldn't fix that because we just don't get it. We couldn't close that loophole. Could a hacker in our system put a message that looks innocuous unless you've been exposed to a certain wavelength that flips that dress to blue and black? Maybe, we don't know. We just don't understand the science well enough. We have some clues, we have a few things, assumptions that we're making that may be leading us in the right direction, but the color science really isn't there. We just don't know enough about colors yet. We don't understand what it is that makes it look different from some brains and others. And look, I've been working on this talk for months. I've been staring at this picture for a month, knowing without a doubt that that dress is black and blue, staring at it over and over, wishing that I could make my brain flip and see it that way. But it is still yellow and gold in my eyes, even though I know, even though I've read all that science, even though I've been cramming my head full of it. It's wild. So there's so much potential going on here in color science and computers. A lot of it's for good. The intersection of tech and color and art can be a vibrant, fascinating, and beautiful place, but we also know that it does have the potential to hurt. So be thoughtful about your application of color, please, in the world. If you're trying to communicate with color, remember that there are many ways to perceive it, which makes it so complex, but there are some guidelines out there to help you. And consider the ramifications if you're building software that provides an experience based on color. I truly believe that we can learn from our mistakes and be better. So go out there and make something beautiful. That's it. Okay. Yeah, I think I have like 3 minutes, so I could take 1 or 2 questions. But yeah, in the back.
Have you seen the research that links color perception and language?
Color perception and language. Oh, I've seen a little bit years and years ago that there is, sorry, the question was, have I seen the research that links color perception and language? And if I recall correctly, there is some research that shows, and correct me if I'm wrong, but there's some research that shows that people are more likely to see, or that if they don't have a word for a color, they don't see it, and then as you increase the language for it, they're more likely to perceive it. Yeah, I don't, the reality is I saw that like many years ago, so I don't have a connection to it here. Yeah, it sounds interesting. I literally had forgotten until you brought it up, and now I kind of want to go check it out and see how it compares to this. But yeah. Thank you, though. That's a good thing to bring up. Yeah, what's up?
Have you seen any of the attempts out of Hong Kong to disrupt?
Yes, I have. So there are a couple. So the question was, have I seen any of the attempts out of Hong Kong to disrupt facial recognition? So there are a couple of interesting ones. One is, of course, they're just literally pulling the facial recognition polls down, which is effective. Yeah, they're also using a lot of lasers and stuff to disrupt the. So what they're doing effectively is that they're working outside the visible light spectrum and using lasers and like infrared and stuff to shine it into the cameras and stuff, right? Correct me if I'm wrong, but I believe that's what I think that from what I have seen. So in Hong Kong, they have facial recognition cameras, and they're trying to disrupt them. By shining lights and lasers at the towers and things like that, and because again, you can work outside the visible spectrum. You can do a lot of the potential here comes from the fact that the things that you can do, the things that humans see and the things that computers see are not the same. So working outside that visible light spectrum, they're doing a lot of that in Hong Kong, because again, they were the ones that had the caps that were shining lights on the face, and so they're also using laser pointers to shine at the facial recognition towers, because then the facial recognition towers can't see your face because they're already I'm detecting the lasers, there's all this light in me, if you are already full of wavelengths. That was a very babbly response to that, but yeah. Great, thanks. All right, I think I'm just about at time. Thank you all for being such a great audience. I did bring some cross-stitch examples down here if you want to take a look. And then also, I have some No Tech for Ice posters. My only request is that if you grab one, put it somewhere where other people can see it. Thank you so much for being so great.